Alright guys, so today we're going to be dealing with examples 9 and 10 in your book. Um, just to get a little bit more practice with friction and one dimension before we go on to the next topic, which is friction on inclines. Okay, so let's see here. For example 9, we're dealing with a problem where we're going to apply a force. And based on this situation, we want to see what is the maximum applied force that we can exert without moving the block. So we want to make sure that we're not moving the block in any way. And we want to exert as large a force as possible. So let's draw a free body diagram real quick. We've got a block. The force of gravity is acting downward, like this. The normal force is going to act upward. Our applied force is going to push the object over to the right. And static friction is going to resist this force over to the left. Some of the things that we know about this object are that its mass is 59 kilograms. The coefficient of static friction is 0.14, and we're trying to find the maximum force of static friction so that we can figure out what is the maximum amount of force that we can apply. The reason that's the case is because if we look at Newton's law for forces, which is that the net force, or the sum of all the forces, is equal to the mass times the acceleration. For this case, we're looking in just the x dimension. So for all of the forces in the x direction, if we add them all together, it'll be equal to mass times the acceleration. If the block is stationary, that means that it's not accelerating. And so this whole term needs to be 0. So the net force in the x direction should be equal to 0. Well, the all of the forces that go into the net force or in the x direction are just the force of static friction and the force applied. So the force applied is in the positive direction. The force of static friction is in the negative direction. And we're worried about the maximum, so I'm going to write max here just to remind myself that I'm trying to exert the maximum or meet the maximum force of static friction here. And we just said that that whole thing needs to be equal to 0 newtons. For the object not to slide or accelerate in the x direction, the net force needs to be equal to 0. To figure out what the force of static friction is, we're going to need to know the coefficient of static friction, which they gave us, but we're also going to need to know the normal force. To do that, we can look at Newton's law for the forces in the y direction. Again, if the object's going to be on the surface and not accelerate up or down, that acceleration should be equal to 0. The two forces acting in the y direction are the force of gravity and the normal force. So in this case, we've got the normal force minus the force of gravity is equal to 0 newtons. If we solve for that, we'll see that the normal force in this case has the same magnitude as the force of gravity. They're just in opposite directions. The deal here is that the normal force is the same as the force of gravity. This won't always be the case. If part of our applied force were in the upward direction, if we had a y component, then we'd be reducing the needed normal force to keep the block from accelerating downward or upward. So you want to be careful about that. If you do have components of your applied force acting in the y direction, your normal force won't always be equal to the force of gravity. In this case it is, though, so we can come back to this equation here, and we're going to say that the applied force is going to be equal but opposite in direction to the force of static friction max. So right now we're just comparing their magnitudes. The applied force then is equal to the coefficient of static friction times the normal force, which we said was the same as the force of gravity. So I could write this out now and see that we've got the coefficient of friction, the mass times gravity, and we can see that the magnitude of the force applied is 81 newtons. That's the max that the force of static friction can supply to resist motion, so that's as hard as we can push without moving the object. Another problem that I'd like to go over is example 10. This example is a little bit different. In this case, we're looking at an object that's already in motion. It's got some velocity pointed to the right. Again, we've got the force of gravity acting on it. We've got the normal force, but in this case, there's a force of kinetic friction that's slowing the object down. And the question asks us, how far will the object move before it comes to a rest? So some of the information that we know here is that the initial velocity is equal to 4.0 meters per second. The coefficient of kinetic friction is equal to 0.05. The final displacement is what we're looking for. The final velocity we know is going to have to be 0 meters per second if this thing will be at rest. They actually didn't give us the mass of the object, and we don't have the acceleration of the object. Let's start by looking at Newton's law in the x direction. So the net force in the x direction is equal to the mass times the acceleration in the x direction. If we look at our free body diagram, the only forces acting in the x direction are the force of kinetic friction. So we can rewrite this and say that the force of kinetic friction is equal to the mass times the acceleration in the x direction. If I solve this for the acceleration in the x direction, it'll look like this. The kinetic frictional force divided by mass is equal to that. Again, because there isn't an applied force, the normal force is going to have to exactly balance out the force of gravity if this object's not going to move up and down. And since it's resting on the table, that's what we would expect. So I can rewrite this then. The force of kinetic friction I can rewrite as the coefficient of kinetic friction times the normal force divided by mass. And then I know that the normal force in this case is going to be the same magnitude as the force of gravity, just positive. So I can rewrite that as just mass times gravity over mass. And so here you can see why they haven't given us the mass of the object. It actually doesn't make a difference in this case because the masses cancel out, and we get that the acceleration in the x direction is just equal to the coefficient of kinetic friction times gravity. Now that I have the acceleration, I can use this equation to find the displacement. I'm going to solve this equation for the final displacement. I'm going to subtract the initial velocity squared from both sides. Then I'm going to divide by 2 times the acceleration in the x direction. The initial displacement we'll just say is 0 since we weren't given any information about that. If I plug in the values that I've figured out so far, the final velocity was 0 meters per second. The initial velocity was given to us as 4 meters per second. The coefficient of kinetic friction was 0.05, and gravity would be negative 9.8 meters per second squared. This will give me a displacement of 16 meters, and that's our answer. These two examples should help you solve the homework problems, which are on page 128, and you're going to be doing problem 44, 48, and 49. If you have any questions, I'll be back at school today after school, so just come and visit me in the lower school science lab.